Hello, guys. Good morning. Good morning to all of you. How are you all? Can you start the session? Am I audible? Just inform whether you can hear me properly. Am I audible? I hope everything is all right. Okay. So this is the third part of the elements of crystallography. The previous two parts we have covered a significant portion. Today we'll be covering the third part. So let us start with this. We'll try to find out the expression for interplanar spacing. So you know that in good morning, Harry. Audio, video, everything is all right, right? Interplanar spacing D, and that spacing is dependent on the Miller indices HKL. So look at this figure. Here we have shown a plane. ABC is the lattice plane, let's say, and as you can see, it is cutting the XYZ axis, means the intercept on the X axis, on the X, Y, and Z axis are A, B, and point C, respectively. We have to find the distance D, which is taken from this point O to this point P on the plane. Okay, this distance D we have to consider. Good morning, Mulli. Now to get the interplanar spacing, what are you doing? We are considering a plane, let's say ABC, with Miller indices. Miller is the name of a scientist, okay? That is why we are using capital letter M here. So consider a plane ABC with Miller indices, let's say an arbitrary Miller indices HKL. Okay. So what we are doing in the reference frame, look, XYZ we have drawn in a very in a unique way. X, Y, and if you rotate from X to Y, it should go to Z. So that is what is happening here. So in the reference frame, draw a normal. So draw a normal to the plane from the origin. And as you can see, it has exactly been done here. From O to P, you can see this is the normal to the plane. So let's say OP be the normal. Let OP be the normal to the plane ABC. Okay. Now you can see different angle. This plane is cutting the x-axis at point O, y-axis at point B, z-axis at point C. OA, OB we have, OC we have. Now this intercept on X, OA, it is making an angle alpha with the normal. The intercept on Y, OB, this is making an angle beta with the normal. The intercept on Z, OC, is making an angle gamma with the normal. This is clear. So let angle POA, that is the angle made with the x-axis, it is alpha. Okay. POB beta and POC, this is gamma. These be the angles made by the normal to the plane with the x, y and z axis respectively. Very straightforward. OP, which is equals to D, this is the interplanar spacing. This is the interplanar distance. Now from the figure, what we can write? From the figure, what you can write? You have to find this D. What is the value of cos alpha? Cos alpha, if you consider this triangle OPA, so what we can write cos alpha? Cos alpha is equals to OP by OA, right? OP by OA. Base by hypotenuse. So OP is D, OA is X. In a similar manner, we can write, okay, some pages should have been kept here, but somehow I did not keep. Okay, let's write a little bit here. What about cos beta? Cos beta is equals to OB, OP by OB. D by Y. And what about cos gamma? OP by OC. OP by OC, D by Z. Can you write it? Okay, you do one thing. You ignore this problem for the time being. You write it from here. DHKL calculation continued. So you see, we could write those things, but from the definition of Miller indices, from the definition of Miller indices, what we can write? Miller indices, we can write, we know for Miller indices we took the reciprocal of the intercepts, right? So if I have H, so it was A by X. Okay, so what is the value of X? X equals to A by H. Similarly, K is equals to B by Y. So Y is equals to B by K. L is equals to P by Z, means Z is equals to P by L. And as a result of that, we can write the value of cos alpha, which was equals to OP by OA. So D by, what was this value? OP by OA. This was D by X. X value we have got. So D by X. So D by A by H. Okay. Cos beta. This is D by B by K. Cos gamma. D by C by L. Now, you know, from the solid geometry, there is an identity. From solid geometry, we can write an identity that if you have a normal like this and they are making alpha angles alpha, beta, gamma with the respective axis, then the square of the sum of them, sum of the squares of them. So cos square alpha plus cos square beta plus cos square gamma. So this is the sum of their cosine square. It should be equals to 1. Okay. So if we just replace this cos square alpha by this expression, so what will you get? D square H square by A square plus D square A square by B square plus D square L square by C square equals to 1. So here you can take D common, D square common. We have H square by A square, K square by B square, L square by C square. This is equals to 1. From this, we can write D, let's say write HKL because it depending on the factor of on the values of HKL. We can write it as 1 upon square root of H square by A square plus A square by B square plus L square by A square. In this way, you can write the interplanar displacing formula. DHKL, a plane with a family of lattice plane with Miller indices HKL. The distance between them is this. You see, when I am writing HKL, so it represents family of parallel lattice planes. So the distance between them is given by this. Okay. Now, this is a general formula. There may be different cases for this. Let's say the case 1, the most popular one, let's say cubic crystal. So what changes will be there in this formula if you consider a cubic crystal? For cubic crystal, you know, all the sides are equal, so A, B, C will all be equal, and as a result of that, you will get the formula of DHKL. So A, B, C, if they are equal, they will come out at from the root. Let's say that is A. A by root over H square plus K square plus L square. Can I write it? Case 2. As I told you, you should have memorized the specification of this lattice parameters. Let's say if I am giving you tetragonal, more than the angles, the sides are important. Tetragonal, you know, for tetragonal A, B are equal, but that is not equals to C. We have this relation, right? So for this, we can write DHKL value for tetragonal crystal. We can write A, B are equal. So 1 upon root over, although you don't need to remember these cases, you need to remember the original formula, then you can easily put if a, b and equal, if a and b are equal, you can write h square plus k square by a square plus l square by c square. Okay, let's say, let's take another case, case 3, orthorhombic. For orthorhombic, what is the criteria? A not equals to b not equals to c. So you see there is a parent cubic, all are equal. Tetragonal, one inequality comes. Here for orthorhombic, none of them are equal. So in this case, the general formula will there will be no change in the general formula, because A, B, C are different. H square by A square, A square by L square, or K square by B square. Plus L square by C square. So I hope you have understood this thing. If you have any question, you can ask. Okay, now you can give this problem a try. A simple cubic crystal with lattice parameter AC undergoes transition into tetragonal structure. Okay, tetragonal, you know what is the formula for tetragonal? A equals to B not equals to C. Cubic, A, B, C all are equal, right? With lattice parameter A tetragonal, B tetragonal equals to root 2 AC. So you can see easily A equals to B not equals to, already given in the condition. CT is 2 times AC. C is 2 times AC. Below a certain diameter, the ratio of the interplanetary spacing of 101 planes for the cubic and tetragonal. So you have to find out the ratio of D cubic by D tetragonal. Do it. Tell me the answer quickly. Could you solve this problem? D cubic by D tetragonal. This ratio you have to find out. Okay. So first of all, for this 101 plane, H equals to 1, A equals to 0, and L equals to 1. So first of all, let's calculate DC. This is, A by root over H square plus K square plus L square. So this is A is equals to, let's say, AC cubic divided by 1 square plus 0 square plus 1 square. So this is AC by root 2. For D tetragonal, the formula is 1 upon square root h square plus k square by a square plus L square by c square. This is the formula, right? So this is equals to 1 upon root over h equals to 1 square plus 0 square by AT BT are same. So let's say, and that is equals to root 2 AC. So root 2 AC whole square plus L is 1 by c square is 2 AC. Okay. So what are you getting? 1 by 2 AC square plus 1 by 4 AC square. 1 by 2 plus 1 by 4, 3 by 4. So 2 by root 3. 2 by root 3 AC. Are you getting this? So what is the value of DC by AT, DC by DT? DC is equals to AC upon root 2, DT is equals to 2 AC upon root 3. So this is equals to how much? Root 3 by 2 root 2. Root 3 by 2 root 2. Now if you take this 2 inside the root, it will be root 3 upon 4 into 2, 8. Option C. Is it clear to all of you? You can give it a try for this problem. The Miller indices of a plane passing through the points having coordinates 0, 0, 1, 1, 0, 0, 1 by 2, 1 by 2, 1 by 4 are. So what it actually asking you? So you have to find out a plane Okay, let's first do this problem, then we'll go for that problem. The lattice parameter ABC of an orthorhombic crystal are related by A equals to 2B equals to 3C. In units of A, the interplanar separation between the 1, 1, 0 plane is. What is given to us? Do this problem quickly. A is equals to 2B is equals to 3C. So let's say if we take A is equals to A, B, how can you calculate B? B will be A equals to 2B, so B is equals to A by 2. In unit of A, you have to find out, means you can understand. It should be expressed in terms of A. So that is why we are expressing everything in terms of A. A equals to 2B, so B equals to A by 2. And A is equals to 3C, so C is equals to A by 3. These three we can write. HKL value are given to you. So what is the value of the interplanar separation? D HKL. This is orthorhombic, none of the sides are equal. So H square by A square, A square by L square, L square by C square, K square by B square. This is equals to H equals to 1 by A is A, K is 0, B is A by 2, L is 1. Why am I making this much mistake? L is equals to 0, A by 3 square. So what is this value? 1 by A square, and this is 4 by A square, and this is 0. So 1 by a square plus 4 by a square, so 5 by a square, so a by root 5. Huh? A by root 5. The value of 1 by root 5 is 0.447. So 0.447 a, that is matching with option A. Clear? Simple problem. So the reason of doing this, okay, I should not omit this. Okay, the Miller indices of a plane passing through the 3 points having a coordinates 0, 0, 1, 1, 0, 0 and half 1 by 4. So look, this problem because I don't have a space here, I'm giving this problem as homework, and you will follow the same process the way we have derived the actual expression of DHKL. Okay, you will follow the same process and you will try to find out this answer. Okay, I think you can easily do it. So you will consider the axis in this way, the way we have done in the first case. So we have the plane, Miller indices of a plane passing through 3 points 0, 0, 1. Let's say this is x, this is y, this is z. Previously we considered a general derivation. Now it has mentioned the points 0, 0, 1 means it is talking about, let's say 1 unit is this. Okay, let's say this is 1 unit is 0, 0, 1, 1, 0, 0. So this is 1, 1, 0, 0 means this point, half 1 by 4, somewhat here. Okay, so it is not cutting the y axis. So you can take the equation of this plane. Let's say this is OA, B, and this point is C, or you can say this is cutting at some point, so you can take that point to be B. So you can take the equation of this plane, x by OA plus y by OB plus z by OC, where OA, OB, OC are the intercept on the XYZ plane. Then you can calculate OA, then OB, then OC. Okay, will you be able to do it? Okay, you will try it at home. If not solved, I'll share the solution. Let's move on. Same procedure. You will start with this, then you will put the value of OA, OB, OC. Okay, you can consider, if you if this picture is confusing, then you can use the last problem. Okay, the derivation image also you can use. Look, once you write the equation of the plane, this is the equation of the plane. Okay, equation of the plane, then whatever equation of the plane you will get, that will be satisfied by this point, because these points belongs to this plane. A plane passing through these points means this point will be satisfied by the equation of the plane. So you will try. You can use this use this image. You can consider the equation of the plane x by OA plus y by OB plus z by OC. Then you will put the values of h, k, l and all, and finally you will check these 2 points. Okay, 1 0 0 0 0 1. Then third point also you can choose. Then you can find out the value of h, k, l. Okay, similar calculation the way we have done it here. Now let us talk about some of the very standard crystal structure. The first one being simple cubic. So from all the standard crystal structure, you need to know few things. Okay, so I will share the PDF, don't worry. So you see, in a simple cubic structure, space lattice is cubic. Atoms are placed at lattice location, therefore an atom at a lattice location will be in contact with the 6 nearest neighbors. This is known as the coordinates number. Number of nearest neighbor, that is known as the coordination number. The coordination number for a simple cubic structure is n equals to 6. This is just an unit cell shown to you. Let's say if you consider any of the atoms, it will be surrounded by 6 more atoms. So you can see, if you consider, let's say this atom, it has, you can see only one atom here, but in the whole lattice there will be 5 more atoms surrounding it. So there will be total of 6 atoms for each atom. There will be 6 surrounding atom, nearest neighboring atoms corresponding to a single atom. And as I told you, lattice is without these atoms. So you can see the black dots, these black circles, these are lattice points, and the big sphere is showing the atoms. So those big spheres are placed at the lattice points. So these are bases and this is lattice, and this whole is the crystal structure. And you can see, although it has shown in a full sphere, the actual picture is this. You see, in the unit cell only this much is contributed. If you consider, let's say this atom, you can see only this much is contributed. Only this much is contributed. This much is contributed. Now, how we get the 6 nearing the coordinate number 6? It has been shown here. So you have taken any of the atom. Let's say this atom you have taken. So the full picture is like this. It has atom towards its left, right, okay, forward, backward, up, down, left, right, forward, backward, up, down. So total 6 atoms you can see. That is why the coordination number is 6. So in a simple cubic structure, lattice constant is the cube edge of the conventional unit cell. Lattice constant means the separation between the cube edge. This is the lattice constant. That value you already know. So this is the lattice constant, that is E. Okay, separation between the cube edge of the conventional unit cell. Thus the lattice constant is the distance between the centers of 2 neighboring atoms. Distance between the centers of the 2 neighboring atoms. A, if you consider this picture, this atom will have radius r, okay, this much. This atom will have radius r. So r plus r, from this center to this center, what is the distance? 2r. So 2r, and you know this center to center distance is lattice parameter. So lattice parameter we can express in terms of the radius of the atom. So A is equals to 2r. Understood? That is why this constant relation A is equals to 2r. R is the atomic radius. Atoms at the lattice location are shared by 8 unit cell. So you can see, let's say this atom, this is the part of this unit cell. This atom is also part of other 7 unit cells. So total 8 unit cells. So this atom is also part of the remaining 7 unit cells. Total each atom is shared by 8 unit cell. Each atom at the lattice location of unit cell contributes 1/8 to the unit cell. So if one atom as a whole contributing to 8 different places, okay, it is contributing to 8 different unit cells equally. So what will be the contribution to one unit cell? 1/8. That is why for corner atom it is taken 1/8. Okay. So the parameters describing this simple cubic is summarized here. You can see coordination number n equals to 6. Number of atoms in an unit cell, only corner atoms exist. So 1/8 into 8, that is 1. That is why n equals to 1. Atomic radius r, lattice constant A is equals to 2r. Volume of unit cell. So if you know the one side, so what is the volume? The volume will be V is equals to A cube. Okay. Volume of an atom. If one of the atom, if the atom having the radius r, so what is the volume? 4/3 pi r cube, volume of the sphere. Okay, the atoms are considered to be spherical. So I hope there is no problem with this picture. So if I just show you one face, if I just show you one face, so you can imagine it in this way, that this is the one face and it has how many lattice point? 4 lattice points will be there at one face, and in one lattice point there will be something like this. So it is difficult to draw exactly, but you try to understand what is actually happening. The atoms are touching to each other in this way. In the drawing I am not able to making it perfect, but you understand, okay, they are touching to each other. So this separation is 2r and this separation is r. Okay. Now we will try to calculate the atomic packing factor. Atomic packing factor, this is in short written as APF, atomic packing factor, and this is written as n effective, number of lattice effective lattice point in the unit cell, multiplied by volume of each sphere divided by volume of each cell. So what does this atomic packing factor exactly means? Atomic packing factor, from this formula you can easily understand that how much the atoms are occupying of the volume of the unit cell, how much fraction of the unit cell is occupied by the atoms, that is the atomic packing factor. How densely packed or how lightly packed the unit cell is. From this value you can easily understand. If this value is high, means more the atoms are tightly packed, the unit cell is tightly packed. So n effective you know already, for an simple cubic, for simple cubic n effective is equals to 1. Okay, for simple cubic n effective equals to 1. Volume of each sphere, volume of each sphere you know, that is 4/3 pi r cube. 1 into 4/3 pi r cube. So divided by volume of each cell is equals to a cube. So there is two way. You can either express r in terms of a, or you can express a in terms of r. Okay, so a is equals to 2r. A is equals to 2r, that means r is equals to a by 2. So we are placing r is equals to a by 2. A by 2 cube divided by a cube. If you do a is equals to, if you put a equals to r, then also this r cube get cancelled. You will get effectively the same result. So from this, how much value you get? a cube is cancelled. 4, 2, 3, 6. So pi by 6. The atomic packing factor of simple cubic is pi by 6, and this has a value of 0.52. So you can write it 52%. The atomic packing factor is 52%. N effective is the number of lattice points. How many number of lattice points N effective? Number of atoms in a unit cell N equals to 1. So one atom at one lattice point. So number of atoms, number of effective lattice points are same. 1 by 8 into 8, that is 1. Understood, Harry? Look, one atom is sitting at one lattice point, means N effective number of lattice points becoming num equals to number of atoms, because one lattice point occupied by one atom. So this is the unit cell. You can see 8 corner atoms, you can see, and these are the lattice points. And you can imagine unit cell is the smallest unit. This unit is repeated, you can see here it is repeated, here it is repeated, here. So one atom is shared by, you can see these many atoms. Just a moment. Hello, गुड मॉर्निंग. कौन सा सेमेस्टर पे हो आप? सेमेस्टर 3. आप लोगों को 11:30 बुलाया है ना? हाँ हाँ, आप आ जाइए 11:30 पौने 12 तक जब भी हो. तो वही सब डिस्कस करेंगे आज, क्या करना है आगे. guys. So you can see this is one of the smallest unit cell, and this unit cell is repeated in this way, making the lattice. So this whole crystal structure is the combination of such numerous unit cell. Numerous unit cell, it is not like that. One unit is getting repeated to make the whole crystal structure. So I think simple cubic you have understood. Body centered cubic. In the body centered cubic, there is just one small addition. Along with the corner atoms, there will be an atom at the body center. So that is the body centered cubic. You see, body centered cubic. Look, remember one thing. Here you can see the atoms are touching along the cube, along the edge of the cube. For body centered, they will not touch along the edge of the cube, but they will touch along the body diagonal, along this direction, because those atoms will be closer. And as a result, this packing will also be different. Okay, don't think that if it is touching in simple cubic, why it is not touching in body centered cubic, because the packing will be different for different crystal structure. In the body centered cubic structure, the space lattice is cubic. Space lattice means the original form. Okay, atoms are placed, the overall shape you can say. Atoms are placed at all lattice location, and there will be an additional atom at the body center of the cubic unit cell. As you can see, 8 corner atoms along with 1 body centered atom which is not shared by any other atoms. These corner atoms are shared by the neighboring atoms, but this one is not shared by any of the atoms. So the contribution will be 1 from this, no, unlike 1 by 8. From face it is 1 by 2. In this structure, the atoms stacked along the body diagonal of the cubic unit cell are in contact. So previously the atoms were contacting along the edge, but now it will contact along the body diagonal, as you can see. So one atom is here with radius r, one entire atom inside the body center, and another atom. So you can see r plus 2r plus r. How much? 4r. 4r. Now you see lattice parameter is same, a. This edge is a, this is a. So what will be this one? This is the hypotenuse. So that value will be root over 2a. Can I write it? Now if you want to calculate this PV, this is also a. So a and this is root 2a. So what will be this? Root 3a. This overall distance will be root 3a. So r plus 2r plus r, this thing is also equals to root over 3a. So 4r is equals to root 3a. So this relation you are going to use while calculating the atomic packing factor. Okay. And here the coordination number for a body centered cubic structure is n is equals to 8. You can easily understand it. N equals to 6 or for simple cubic. Now 2 additional thing will come because of the body center atom. So total coordination number will become 8. For BCC it will be 8. Simple cubic 6, body centered cubic 8. Now here the effective number of atoms in the unit cell for BCC, if I calculate the n effective, so you know the formula, actual formula is 1 by 8 into number of atoms at the corner plus 1 by 2 number of atoms at the face plus 1 into number of atoms at the body center. Okay. Corner. So here how many atoms in the corner? 8. How many atoms at the face? No atom at the face. How many atoms at the body center? 1 atom. So 1 plus 1, that is 2. Okay, n effective is equals to 2. And what about r? 4r is equals to root 3a. R is equals to root 3 by 4 times a. So what is the atomic packing factor for BCC? We know the formula, n effective into volume of 1 atom. N effective is 2, volume 4/3 pi r cube, r is root 3 by 4 a whole cube, divided by volume of the unit cell, that is a cube. Okay. So what are you getting? This is equals to root 3 by 8 into pi. Root 3 by 8 pi. If you calculate this, you will get 0.68. So this is 68%. So you can see it is comparatively more tightly packed. Is it clear, guys? Tell me. Now the parameters describing the structure of a body centered cubic are, so you know, first of all, coordination number n equals to 8, that you know. Number of atoms in the unit cell n effective, that is equals to n effective, n equals to 2. Okay, atomic radius r, lattice constant a is equals to 4 by root 3. Look, r is equals to root 3 by 4a, and from here you can write a is equals to 4 by root 3 times r. Okay, so that is why 4 by root 3 times r it is written. Volume of the unit cell a cube, volume of an atom 4/3 pi r cube. Okay, and how coordination number is 8, it is shown here. You can see this body centered atom, if you can take, if you take the body centered atom, it has nearby 6 atoms, 1 2 3 4 5 6 7 8, and that makes the coordination number n is equals to 8. Okay, so is there any question from body centered cubic? Now nearest neighboring atom means the closest one. For simple cubic, you know, the closest one was this, no confusion in it. Corresponding to this, the nearest atoms are this and this and this. And for the other unit cell, we have, you can see this nearest neighbors atoms are shown here. Now for body centered cubic, you see the nearest neighbors, this, 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 this. In two-dimensional picture, it is showing that they are different, but if you consider 3D, they will be same. Atomic radius, any atom has a radius r, na? Atomic radius r. But lattice parameter a is different. Okay, previously a equals to 2r, but here you can see here 4r is equals to root 3a. A is equals to 4 by root 3 times r. A is the lattice parameter. Okay, volume of the unit cell is a cube. R is the radius of the atoms. So don't get confused with A and R. A and R are different. Okay, so what I was talking about, nearest neighbor. So for body centered cubic, you see the nearest neighbors are these corner atoms. Okay, second nearest neighbor, you can see if you consider this atom. So the second nearest neighbor will be these atoms. Okay, third nearest neighbor will be these atoms. If you consider this, third nearest neighbor will be this. Look, I am just showing you one case. If you consider, let's say this 8th atom, first nearest neighbor will be this body centered. Second nearest neighbor will be atoms like this or this. Third nearest neighbor will be like this. Okay, now so that is what it is asked here. The third nearest neighbor distance in a BCC body centered cubic crystal with lattice constant A0 each. Can you tell me? Simple, you can do it. C, root 3a. Very good. This is the body centered atom. Okay, so let's consider this atom to be the reference atom. So first neighboring distance, if you want to write, because it has asked third nearest neighbor. So first nearest neighbor distance, let's calculate. First nearest neighbor distance. What is the first nearest neighbor distance? This is equals to how much? If you consider this atom, first nearest neighbor distance is this. Now to reach to that point, you need to consider the body diagonal actually. Okay, so first nearest neighbor distance, you can also imagine it in this way, that this distance is same from this. So if you consider, let's say this is 0 0 0, okay, this is 0 0 0, this one will be a naught 0 0, because the lattice constant is given a naught. So what will be the coordination of this? Coordinates of this will be a naught by 2, a naught by 2, a naught by 2, right? And as a result of that, first nearest neighbor distance will be the root of a naught by 2 square plus a naught by 2 square plus a naught by 2 square. So this is equals to root 3 by 2 a naught. This is one way of doing it. Another way you can do it, you can easily calculate a naught square plus a naught square equals to root 2 a naught, then again root 3 by 2 a naught. Second nearest neighbor. What is the second nearest neighbor distance? For this is the first one, first nearest neighbor. Now second nearest neighbor is this. Okay, let's say if I show it in this way, this is the second nearest neighbor. Second. So you can see easily that this distance is a naught. Third nearest neighbor distance, third will be this one, will be this one, third. So a naught plus a naught, so it is root 2 a naught, right? So depending on the question you will answer. Next, face centered cubic. This is also an important crystal structure. In FCC structure, one atom lies at each corner, and you see no body center atom, only atoms at the face, and the atoms will touch along the face. You see, for simple cubic, the atom was touching along the cube edge. For BCC, the atoms were touching along the body diagonal, but for the face center, the atoms are touching along the face. So this face has been shown here, as you can see. So the separation between these two atoms is A, you already know. So A. So what will be this distance? This is R, and this is whole atom 2R. This is half atom R. So 4R, that is equals to, you see, root 2 A. Can I write it? So from this, R is equals to root 2 by 4 times A. So this is equals to A by root 2. Now what will be the atomic packing factor for this? Let's calculate the atomic packing factor for this. So for FCC, what is the value of N effective? You know, 1 by 8 into corner atom, 8 corner atoms are there, plus 1 by 2 in the number of facial atoms. So how many atoms are the face? 6 faces, 6 atoms. half into 6. Is there any atoms at the body, inside the body? No. So this is 1 plus 3, 4. Okay, 1 atom at each lattice point. So that is the number of atoms in the unit cell is 4. Okay, so what is the atomic packing factor for the FCC lattice? It is N effective into 4/3 pi r cube. R is equals to, we have already calculated, R is equals to A by 2 2. A by 2 2 divided by volume of unit cell A cube. So this will give you root 2 by 6 times pi. So this is 0.7. So this is more densely packed as compared to simple cubic or body centered cubic. 74%, simple cubic 52%, body centered cubic 68%, and face centered cubic 74%. So this is more closely or tightly packed. And the details you can see here: atomic radius, lattice constant, volume of a unit cell, volume of an atom. Now coordination number you can see here, it is 12. So corresponding to one atom there are 12 neighboring atoms, and you can see it in this picture. So here 1 2 3 4 4 4 8 unit cells is shown. So you see, this is one of the unit cells, this is one of the unit cells. So one atom at the corner here is taken as a reference point, and you can see this point is surrounded by 12 nearest neighbors. Okay, so number of first nearest neighbor is 12, next nearest neighbor is 6. Okay, so that is why the coordination number of FCC is 12. I hope this is clear. I'm giving you a question. Atoms which can be assumed to be hard sphere of radius r are arranged in an FCC lattice with lattice constant A, such that each atom touches its nearest neighbors. Take the center of one of the atoms as the origin. Another atom of radius r assumed to be hard sphere is to be accommodated at the position 0 a by 2 0 without distorting the lattice. Means you cannot force the maximum value of r by r. Okay. So here the atomic radius is given to be capital R. So what is actually telling you? You have to accommodate a new atom of radius small r at 0 a by 2 0. Okay, 0 a by 2 0. So if you consider this to be 0 0 0, this is a 0 0. So halfway here it will be, or 0 a by 2 0 means it is talking about the here actually 0 a by 2 0 means it is talking about here. So now this is 0 a by 2 0. Now if I just show you this one line, we are showing you this one. What is this coordinate? 0 a 0, right? So we have the situation like this. Let's say these two atoms are situated at the cube edge. Okay, this radius is given to be capital R, this radius is given to be capital R, and you know this separation is A. Now you have to accommodate an atom in between this without distorting, means it will be something like this, and it has a radius given to be small r. So this is the location of, let's say, 0 0 0, this is 0 a 0, and this location is 0 a by 2 0. Okay, so you have to find out this radius. So obviously from the figure we can say you have to find out small r by capital R. This is the ultimate thing you require. So from the figure, what you can write? A is equals to capital R plus 2r, no, this is r also, this is r, 2r plus this is capital R. So this is 2 into small r plus capital R. Let's say this is equation number 1. Now for FCC, you already know that the atoms touches along the body diagonal, sorry, atom touches along the face like this. If you consider this is one face, then we have the atoms here, okay. What is this distance? If this is a, this is a, this is root 2a, and this distance is 4r, right? This distance is r, 2r, this is 4r. They have taken the radius of the atoms to be capital, that is why we are taking capital R. So 4r is equals to square root of square root 2a. So from here a is equals to 4r by root 2. Let's say this is equation number 2. So if they both are equal, so we can say from equations 1 and 2 we get this is 2 root 2, so 4r by root 2 is equals to 2 into r plus capital R. This 2 getting cancelled, so what are you getting? Root 2 capital R is equals to r minus capital R. Sorry, so root 2 minus 1 capital R is equals to small r. It is talking about, sorry, small r by capital R. Okay. Therefore small r by capital R is equals to how much? Root 2 minus 1. The value of root 2, 1.414. So 0.414. This is matching with option. Is it clear? So I think this is enough for today. We'll continue the next part. One more class is required to cover the crystallization. It's a huge topic actually. 4R? 4R how? So it is like, you see the atoms are touching along the piece. So let's say, okay, one atom here, this is the actual scene. ये छोटा कैसे हो गया? So you imagine it in this way, that here the radius is r, here whole atom is there, so this is 2r, here half of the atom is here, so r, so r plus 2r plus r, that is a 4r. Center to center distance become 4r. Now you can see this is how it is 4r, r 3r 4r. Here in the question they have said you that you have to take capital R, that is a 4r. And why root 2a? Why this root 2a? Because this distance is root 2a. A, this is root 2a. From this we get root 2a. From the radius perspective we get 4r. Is it clear, Harry? Chalo, let's end the session here. Thank you guys. Thank you very much. See you in the next class. Bye bye.